So today we're going to start a new topic. And broadly speaking, I just call it the definite integral. And this is going to be really the second main application of the integral, right, or the antiderivative. So far we've used it to solve differential equations, right? We've shown a lot of differential equations and how useful it was to be able to take antiderivatives. And in my opinion, that is, really the best application today of antiderivatives. However, a very classical application of them, and one which, of course, is still important today, is out of the definite integral. And, well, maybe the first intuitive description of it is it's a way of computing areas. Okay. So the Greeks, for instance, knew how to find the area of a square, as you have a pretty good idea how to do. They even were clever enough to find the area of a circle. So already this is a little bit complicated, right? But if, for instance, you drew this classic picture from calculus textbooks, right, and said, let me see, what if I just want to measure the area of this thing that looks a little bit like pi? Kind of like pi. Let's say I just wanted to measure this area. Now all of a sudden this has become a very tricky task. Okay. But there's some things we can do to try to attack this problem. But let me give you first a more general looking picture, because already this is very suggestive of where we might try to go. I got coordinated axes, right? I have this curve on top, and of course a curve is always going to suggest, that I should give it a name, and it could be a function. And now all of a sudden, those of you who've taken calculus before are probably thinking, I know where this is going. I know how to do it. So let's draw first a more randomized looking picture, right? A more random picture. Let's say I wanted to compute the area of this region. So how would you try to do it? Now, let's say you had to paint this thing, and you needed to know exactly how much paint you needed. I know the administration will get very upset if you paint on a chalkboard, so this is a thought experiment. Related rates. Explain. You're talking to my collar here. Sorry, nobody can hear you. I just remembered this. Okay, so no, say it again and I'll repeat it. Okay, so you're thinking, like, you know how much you're using in a brush stroke and see how long it takes you, or no, you're... Oh, how long it takes. Okay, so for instance, if this was a pool, and you wanted to know how much water was needed for the pool, you'd just get a flow meter and see how much was going in and count how long it took and then multiply and you know how much is in there, right? Okay, so that's what you're saying. Well, let's say you have to buy the paint before you can paint it, and you don't have enough money to buy any excess paint. You only have what you have, and so you need to know ahead of time how much paint you're going to need. So your idea is good, but now I'm adding more restrictions. Try to suppress good ideas. That's what I do. Yeah. Separate it into different curves. Oh, okay, so you mean something like this. Okay. This way too? Okay, so now what would I... Okay, I'll call that X. I'll call that Y. Would it help if you had chalk? values.
You can set up an integral because this is area. So if this is like degree, and you have to know this function.
I don't know what that symbol means.
I can't do it. Okay, no. Okay. Integral.
Yeah?
It's like 0 to 5.
I don't know what that means.
Okay, it's like you're making me so cool. It's like
Mind you, I'm assuming, even though I know people have pre-knowledge,
okay, it's like
that we don't know what these things mean yet.
area inside the curve because an integral is the sum of. It's like
What?
this is so hard.
It's okay. It's okay.
It's like the area inside of a curve because you're adding up each thing inside.
What are those things that you're adding up?
Like the function value at each point.
So where?
Change in the function value.
So here I have a problem, right? Because, for instance, this isn't a function, right? It doesn't pass the horizontal or the vertical line test.
Well, like you divide it even more.
Okay, so you're thinking I have to really divide these things even more. And
Yeah, until you have a function for each portion of it.
And how would that integral, I mean, how does that integral work? How does it actually
Because
give me an area?
It's the sum of all parts inside of an area. Inside of it's
How does, yeah.
It's like no, let me think about it.
No.
Okay. Well, when we do an integral, it adds up at every given value.
Tell me, I don't know what that means.
Okay, I'm just in the wrong paper.
No, this is good. This is good. What do you mean it adds up at every given value?
Like an integral is the change in
And when you say change, I think derivatives.
yeah. Well, but it's
No, anti-exactly.
it's inside of it. Instead of adding up, we're taking the general function.
No,
I'll
it's
think
okay.
about it.
Okay, it's okay. No. I appreciate the effort. And
I think I explained it.
no, okay. So of course, if you've seen integral calculus before, you have some idea about what should be happening, right? Okay, this integral should be telling me the area. Okay, but how is it actually doing that? Well, let's say I take this idea of drawing these little lines, right? But instead of just leaving them as such, I start drawing grids. Like this. Okay. And now let's say instead of partially college educated, certainly high school educated students, you were 7 years old. And you were sitting, as I was many, many years ago, in your elementary school, taking some state-mandated test. And they asked you, given this picture with this grid, how would you compute the area? Right. Okay. So assuming, of course, that I drew this grid in a very nice, consistent way, right? You actually had squares. Yeah. Okay. So certainly, you know that the squares which lie completely inside of the region, you just count those up, right? You know, and maybe we draw these so that each one has area 1. Okay. Fine. But then, of course, you have a problem because you have these partial ones, right? That it just intersects them a little bit, and the way that it intersects them is not some nice region. Okay, it's not like, oh, well, it's clear that if I add up this one and that one, that I get a full square. You know, that's really tricky. Right? So how might you at least get an approximation? We could put other rectangles in the little rectangle. Sure, you could start breaking it up, right? That's one excellent idea. Well, let's say we want to stay consistent with our, just for now, with our grids. All right, we only want to keep. We draw this grid. It's already on the paper, and we want to get an estimate, right? Say a lower bound and an upper bound. Right? How could we bound? So somebody says, well, what's the minimum amount of area you have in this thing? Right? What could you do? I mean, here's an easy one: 0. Right? That is a perfectly legitimate lower bound. Is it a good lower bound? No. Why not? Because any idiot can see there's more than 0 area in this thing. Okay, fine. So what's a better upper bound? Well, 1. Okay, that's a better upper bound. Is it a good upper bound? No, because any idiot can see there's more than 1 square completely inside of this thing. So without having to do anything tricky, what's the best lower bound that you can think of? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I'm still having all these lower bounds. Are they getting better? Sure. Okay. And at what point would I have to stop this process, assuming I didn't want to do anything tricky? Yeah, you count all the full squares. Right? Okay, so that would give me a very good lower bound, and nobody would come by and say, well, geez, why didn't you just do this to get a better lower bound? Because there's not a whole lot you can do for these weird regions right at first. Okay, I mean, it's not clear. It's not obvious what you can do. Okay, so fine, you have this nice lower bound on the area. How would you get a good upper bound on the area? Count the partial ones as whole ones, right? So you count all the ones that are already inside, and that gives you your lower bound, and now take all these partial ones and just, well, imagine they were all whole ones. That's certainly going to be too much, but it's also going to give you an upper bound that is reasonable, and that nobody can say, well, geez, you clearly can get rid of this amount of area from that. Okay, so what's the problem? Well, the problem is not that we're getting the wrong answer. I mean, we know we're not going to get the wrong answer when we approximate. I mean, we're not going to get the right answer when we approximate. So that's really not the problem. Right? What's the problem as far as trying to get a good approximation? Well, the problem is our squares are too what? Too big. Yeah? If we made these squares smaller, well, everything on the inside, right, the interior of this area that doesn't sit around on the border, well, that's not going to change anything. Okay? But if I make these regions smaller, what's going to happen to my estimates? Yeah, they're going to get better because you're going to be able to fit some full squares inside of the region. Right? So your lower bound will get a lot better. And you're going to be able to exclude some full squares from outside the region. And so your upper bound is going to get a lot better. Right? Okay, so fine. So you would just start going through and drawing more lines and making a tighter and tighter grid. Okay, let's make it even more complicated. Okay. Let me draw, this is where me deciding to do integral calculus is really, multivariable integral calculus is really going to bite me. I am the world's worst artist. Okay, so but I'm especially in 3 dimensions. Especially in 3 dimensions projected onto 2 dimensions. Okay, so let's draw an artist's depiction of 3 dimensions. No? Is that roughly? Yeah, I see. Okay, so that's going back, and this is coming out of the chalkboard. No? Okay. And now let me draw a surface. Actually, let me even make it nastier. A square is just somehow too easy. Okay, so this is a region very much like this region. Okay, and let's say just for now that it's lying in a plane. Right? That you could draw. There is a plane that goes right through this surface. Okay, it doesn't curve a whole lot. Okay? And by say a whole lot, I mean at all. So it's nice and flat. Okay. Now, let's say that for every point on this region, right, well, a point on here looks like it has a coordinate, x comma y comma z, right? Usually I think this is the x-axis. I know this is weird. He changed all the orientations of the axes. This is the y, and this is usually the z-axis. Right. Okay, so I can specify any point anywhere, right, and it's called 3-space, by a coordinate, x, y, z. Okay, fine. And let's say I now have a function, and it's not just a function of x anymore, but it's going to be a function of x and y, and it's going to spit out a z value. So I have some function that looks like z equals f of x comma y. Okay, so it's no longer a function of one independent variable. It has two independent variables. Okay? I have to give you an x coordinate, and I have to give you a y coordinate, and when I give you that, this function will spit out a z coordinate. Okay. So what that means is for every point in this region, I can specify, right, another point. Right? I'll just forget about the z coordinate. I just look at the x and the y, and it'll specify another z. And if this function is sufficiently nice, right, maybe I get some nice thing which hovers over it. I wonder if I need to. Yeah, I probably need to change the. I need to make this flatter. So over it, I'm going to have some nice surface, okay, which sits on top. Okay, so if that was your x, y, z, this would be f, maybe of x, y. Okay, it doesn't have to lie right above it. It just this point goes into the function and spits out some value. Okay, and if the function is continuous in some nice way, right, then okay, it's going to build some surface, okay, that sits, you know, over here. Okay. Now let's say I wanted to compute the volume of the region. So this is, you think about this as, think of it like a pool. You have a nice pool in your backyard, and on top you have maybe an awning or something that goes above it. And I want to know how much volume is contained under my awning. Okay, and let's say that the awning is somehow, the shape actually matches the shape of the pool, which is kind of weird. Okay, so it's cut in exactly the same. So even this might match, you know, the right shape somehow. Clearly. Let's say I wanted then to compute this volume. How could I go about computing a volume? Well, over here we said, well, we want to use maybe squares or more generally rectangles. Right? We know how to compute the area of those. That's very easy. Right? Now, in 3 dimensions, how would you want to compute volume? Well, what's probably the only thing other than a sphere? The only thing you know how to compute the volume of. Cube, or more generally, the rectangle version of a cube, right? So you might call it what do they call it? A rectangular parallelepiped or something. Right? Okay, it looks like this. This is going to end up in one of those Escher drawings where the legs connect to the wrong, wrong place. You know what I should have done? You get the idea, right? It's a nice rectangular bit, and you can compute the volume, right, by, if you call this, I don't know, the width, and that's the length, and this is the height, you just multiply the two together. Now you know the volume of that thing. So how would I compute the volume of the region, right, which is under this nice surface, but over this nice region? Well, instead of drawing a grid in 2 dimensions, why don't I draw a grid in 3 dimensions? Right? I'll start drawing these lines like this, and I'll build a whole bunch of these little parallelepipeds that go up from the bottom and head up to the top, right, and fill up this whole thing with them. Right? And some of them maybe are going to be too big. Right? They're going to be too high. They're going to capture too much volume. And some of them are going to be too small. They're not going to capture enough volume. So I'll get a lower bound and an upper bound. Right? Exactly the same sort of situation. So all of these problems, right? And by the way, doing this one gives you a pretty good idea how to do this one now, don't you think? Yeah, how do you think we should compute this area now? Doesn't it look much easier? Right? You can start drawing some. I mean, actually, you don't even need to draw a grid. You can just start drawing these little rectangles here. Right? And maybe you do something like this. Right? And now you have a bunch of rectangles. Right? If you add them up like this, all right, they're all somehow missing a little bit. Well, maybe not all of them. Most of them are missing a little bit of area. Okay, fine. So you're getting probably a lower bound. It's not correct, right? You could also, draw it like this. Right, drawing it the other way, and maybe now you're getting more of an upper bound. Okay, so it's a little bit too much. But if you wanted to get a better approximation, what would you do? Okay, that's an interesting idea. Take the average, right? Take the lower bound, the upper bound, take the average. But how could I get a better lower bound and upper bound to start with? Okay, I could try the middle, right? Instead of looking at drawing from one end point to the other, I could do the middle. Right? That's one way to do it. What if I did not fix? I mean, here I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 rectangles. What if I don't fix that number? Can I do better? Well, infinite amount is tough, yeah. I don't have that much chalk, and it's not thin enough. Yeah, but okay, but more rectangles, I get a better approximation. Okay? And over here, more of these grid lines, right? I'm going to get a better approximation. Right? And over here, more of these parallelepipeds and thinner ones, right? I'm going to get a better approximation for this volume. Okay. At least in the start, I want to focus on these two. Right? This is going to be solved using, as many of you know, an integral, a definite integral. This is also going to be solved using some version of it, only it will be called a double integral. It's not the only way to do it. In fact, you can fiddle around, as Dina actually was trying to do, and solve it with a simple integral. Right? But it's going to turn out that a more natural way to do it is going to be with a double integral. Okay. But the reason why I want to show them to you all at once is really that it's the same idea. Yeah? And once you see one, you can do the other. And there's no reason to hold it back. These aren't state secrets. All right. Okay, so let's start, though, with what is now. Doesn't this look a lot easier after drawing these pictures? So I'm really going to do the easy stuff first. Okay, so let's start with the easy situation. So let me redraw the picture. Okay. And for now, we're doing everything in the first quadrant. Okay, and we're only doing that for convenience, because if we're talking about area and we went into negative quadrants, we can potentially get negative area, which is fine. It's just not good for our intuition, and so we would want to put absolute values everywhere to get rid of that problem, and that would just make all these computations kind of annoying. So we're just going to skip that. Okay. So I'm going to look at an interval A to B. And I'm going to have a function which is defined at least on A. I don't care what happens. and I want to compute the area under the curve but above the x-axis. Now, what we just said is one very nice way to do this is to draw rectangles. Yeah? Okay, so we draw these nice rectangles. We can get a lower bound, right? We have to choose somewhere to start drawing the top of the rectangle. So I suggested maybe the right side. Then I suggested the left side, right? Maybe Lath suggested both ways. Right? That would be the average. Jenna suggested go right to the middle. Okay, so you have a lot of different choices where you can draw the top of your rectangle. Okay, but first we actually have to write down our rectangles. So to do so, we make the following definition. So let AB be an interval. Well, a partition of AB. Okay. Well, what do you think about? What do you think about when you hear the word partition? What does it mean to partition something? It doesn't mean to determine the area. So to separate, yeah, partition, right? It has the word part in it, yeah? Okay? You break things up. Okay, you partition, you break them up. Okay? So I'm going to break up this interval. That's what a partition is going to be. It's going to be a way of breaking it up. Okay? So the way I'm going to write this, a partition of AB is a set x0, x1, xn, which should be a subset of this interval. So all these are a bunch of real numbers, okay? And they're all contained in this interval. This little symbol here means is a subset of. Right? They're all in the interval, such that x0 is less than x1, is less than x2, is less than xn. Okay. But this wouldn't be quite enough to be a partition of all of AB. Why not? Remember, so I have this interval, right? Think of a nice line, and I want to partition. I want to break it up, right? And somehow I'm breaking it up, right? Things between x0 and x1 and x2, and so forth. But what do I really want to do? Well, if I did this, I'm somehow missing all the stuff on the side. I'm missing everything before x0, and I'm missing everything before after xn. Okay, I'm losing part of the interval AB. Okay, now, of course, then you can just say, fine, just stick A on the end and B on the other end. And, well, that's exactly what we did. We just assume that this x0 point is n. Right? It's your endpoint. And this xn is b. Okay, so every partition always starts with a and ends with b. Okay, and what does a partition look like? Well, it looks like this. There's x1, x2, x3. Notice I'm not making these regular. The spacing is off. And it's not just because I'm incompetent. Partition. So this would be a partition of the interval AB. It has nothing to do with this. Just a partition. You're just breaking it up. Okay, now my rectangles are going to go right in each of these partitions. So I could now draw up this line. And if I do so, I don't have a rectangle, right? Because of this nice curve on top. So I now have to choose right? Where I'm going to put my top of my rectangle. So I really have a rectangle. So I can put it down here, but now my estimate is really bad, right? So you thought, okay, well, you could put it here. And now you're missing some area, right? You miss all this garbage at the top. Or I could put it up here, and now I get all this extra garbage. Or I could choose, say, the midpoint, and what would I do? What do I do if I'm going to choose? Yeah, so does it really mean the midpoint between A and x1, or actually I could choose the midpoint from here to here, right? So I could go in the middle and draw that. All right, and now actually that's not so bad. I really don't get a whole lot of extra stuff, but I mean I'm missing a little bit. But they cancel out actually a little bit. You know, I get a little extra, I get a little, okay, so that's not so bad. Okay, but you know, somebody else is clever. Shirley is clever, and Shirley says there's a much better point up there for it. Right? And so I give her the chocolate chip and say, look at this one. This one, yeah, you get a lot of extra area and a lot of missing area, but they cancel out completely, right? Perfect. So here's the thing: you can choose any point, that you want. You can make it any height that you like, right? We could have made it down here. We could have put it up here. We could put it there. We could put it there. We have our choices. Okay. So we're not going to make a choice. That's my point, right? Because you always have these choices, and so we're just going to pretend that you don't even make a choice. Okay. You just make a whole bunch of. You just pretend, okay, well, I made a choice there, I made a choice there, I made a choice there, and I can make different choices for each choice. Okay, whichever one is the best. If Shirley finds a good one for the first interval, and Jenna finds a good one for the second interval, and Highway finds a good one for the third interval, we can make all those choices. They don't have to be consistent. All right, so what am I going to do? Well, in between, right, each of these, in between each of the points in our partition, I'm going to choose some other point. And call it, this one will be called C1. Right, or maybe C0. That'll be, because this came from X. And I can go up to the curve. And the curve is, well, if the curve is f of x, then this point is f of C0. So at some point on the curve. And I'm going to choose that as the height of my rectangle. Okay, but I don't have to specify what that point C0 is. That's why I say I don't make a choice. It could be anything you want. And so then, okay, I'll go over here, and this will be my C1. So I can draw my line coming down, and I'll go up the curve. And there's f of C1, and that's the height of my rectangle. Okay, that's actually pretty good over there. And then I come over here, and I draw my line down, and I choose a point in the middle. I call it C2. And again, this is not a bad little region here. My rectangle is to that point, and I'd only miss a little bit. I go to the next one. There's my C3. My line going up. Okay, there's f of C3. All right, this rectangle is not as good. Right, it captures, it's missing a little bit, but it's capturing a lot more. And then I can do it over here. Okay, there's my C4. F of C4. Draw that point. And then this will be C5. F of C5. Okay, and I can draw that rectangle. Okay, so I'm no longer asking the impossible question, what's the area under that curve? I'm now only asking you the very easy question, what is the area of all of these rectangles? Well, let's start with one of them. What's the area of this first rectangle? X1 minus X0 times f of t. Okay. It's the base, which is X1 minus X0, times the height, right? And the height was f of t0. You happy with that, Hussein? Okay. And so that's the first one. Okay, what about the second one? What's the area of this rectangle? X2 minus X1 times. Okay. It's easy, yeah? This is clear. It's just the base times the height. The base, right, is just the width. The width here is how far you had to go from x1 to x2. How do you get that? You do x2 minus x1. Right? If that was 3 and that was 5, it'd be 5 minus 3. Right? What's the height? The height is just the value at c1, right, of the function. Okay, it's easy to do this. Okay. Now, we get tired of writing this whole x1 minus x0, x2 minus x1, and so forth. So we give a special name to the width of each of these intervals. I'm going to call this width delta x0. Okay, so delta, remember, means change. Okay, so in this case, it's meaning the change from x0. Okay. So the way I could write down the area of all this is I could write delta x0 f of t0 plus delta x1 f of t1 plus and so forth delta x, let's see, what's my last one? 5 f of t5. And this would be a very reasonable approximation of the area under that curve. Now, the problem with writing things this way is it takes, a lot of effort, and this 5 could have gotten a lot bigger, and then you're missing a lot of things, and it doesn't look very slick, mathematical. So how does the mathematician start to write this down? Well, we use the summation notation. So recall. Oh, 10. Oh my goodness! Oh, I'm so sorry. I was thinking we were going to 11:15. Okay. Very good. Very good. Yes. So tomorrow. Thank you for. Yeah. Tomorrow we will learn how to write this down in a much more concise way. Very good. Very good. Yeah. Okay.